Welcome back, everyone. In this video, we're going to continue Chapter 3, looking at electron configurations and the periodic table. Let's begin. So just to remind ourselves that when we have a single electron atom, such as hydrogen or helium plus or lithium 2 plus, etc., that those will have energy levels that are only as a function of our n value, the principal quantum number n. However, due to shielding, we see that there is a splitting of energy levels within a shell such that the orbitals within a given subshell are degenerate, as is depicted here. Those 5 have the same energy level. However, those orbitals within that are not in the same subshell but same shell, such as the 3p versus the 3d, those are not degenerate. Those do not have the same energy level. And again, that's due to the core electrons. If we have our nucleus and we have our core electrons, they shield outer electrons and they reduce the effective nuclear charge. So because the orbitals, because they have shifted energy levels, we can apply what's called the Offbow Principle, which is German for building up, to come up with our electron configurations that describe the lowest energy state. So the Offbow Principle says specifically that when an electron or an element is in the ground state, the orbitals fill sequentially, starting with the lowest energy orbitals first. You see this image in the ebook, and this describes the pattern. Remember that we have to, the energy levels is a function of both the n value and then also the L value. So L increases here to the right and N increases as we go down in this image. And so determining the energy is what is depicted here. Okay? So if we look at the hydrogen atom, the ground state is with the hydrogen atom in the 1s orbital. For helium, it's to put the electron in that same orbital to fill it. We want to fill the lowest energy orbitals before moving on to the next highest. For lithium, the next highest energy orbital is the 2s orbital, so we fill that one first. Then for the next element, beryllium, we want to fill up the 2s orbital before moving on to the next highest energy level. And that brings us to boron. With 5 electrons, it puts its 5th electron into the next highest up energy level. And these are all ground states. These are the lowest energy levels possible. And any configuration that's not following the Offbow Principle is in an excited state. So for example, if we were to take hydrogen and we put the electron, instead of in the 1s, we put it in, let's say, the 2s. That's an excited state. Or if we put it in the 2p, that's an excited state. So for boron, we could excite any one of the core electrons. Let's say that we take this electron and we excite it here into the 2p. We would have then 1s1, 2s2, 2p2. That's an excited state. And just to make sure that it's clear, as we're designating the electron configurations, this is our n value, this is the L value, and this is the number of electrons in the subshell. There's another rule that dictates the lowest energy states, and that is Hunds Rule. So electrons, once we get to carbon, we have a scenario we have to deal with. We have 6 electrons. And so the question of what is the lowest energy state of those electrons? Hunds Rule is what we use to determine what is the ground state within a subshell that has multiple orbitals. So remember that within the 2p subshell, that all three orbitals here are degenerate. So it doesn't matter which electron we put them into first. However, Hunds rule does dictate, in order to minimize the electron-electron repulsions, that we're going to do two things. First, we're going to partially fill the orbitals, and then those orbitals must follow with the same spin. So to give an example here, again, for carbon's electron configuration, the top and the bottom are both equal in terms of their energy. The reason for that is because we have separated the two electrons into two different orbitals. We want to put them in orbitals with the same spin. That is essentially what we're looking for here. And so there's two criteria that we need to consider. We need to put them into different orbitals, and then the spin is to be considered as well. So we could also violate Hunds rule if we did the following. So the middle one violates Hunds rule because these are in the same orbital when they could be in a different orbital that has the same energy level within the same subshell. This is violating Hunds rule because these have opposite spin. We need both of those things to be true in order for it to be the lowest energy configuration. Now let's talk about a simplified way of expressing the electron configurations. This is done by abbreviating the core electrons. So if we take a look at the element neon, its configuration is 1s2, 2s2, 2p6, meaning it has 2 electrons in the 1s orbital, 2 in the 2s orbital, and 6 electrons in the 2p orbital. We can abbreviate that simply as Ne in brackets because it is a filled shell. Then, for any element that comes after it, we can abbreviate that inner filled shell by using neon's symbol with the brackets. So when we start a new row in a periodic table, instead of writing out the full electron configuration, we can abbreviate using the noble gas core electron configuration. And so we see that greatly simplifies the electron configurations. Once we get to a new shell and we completely fill the shell, that becomes part of our new core. And so argon, which would have neon 3s2, 3p6, we can just write as argon. And so then when we start a new row on the periodic table, we would use argon as our new core. And so you want to be familiar with and able to use both the abbreviated and the extended electron configurations. This is indicating that the inner or core electrons are indicated by that noble gas configuration, and then the other electrons are what we call our valence electrons. These are the electrons that actually do the chemistry, and we'll talk more about those later. Let's now move to the transition metals. So the transition metals behave a little bit differently than the non-transition metals. And that's because when we take a look at the energy level diagrams, if you remember, by the time we got to the 4s and we looked at the 3d electrons, that the energy level, the energy difference between those subshells is very, very small. And so when we look at the electron configurations of certain transition metals, those being chromium and copper are the two that you need to be familiar with, they have exceptions to the Offbow principle. We would expect for chromium to have argon 4s2, argon 4s2 3d4. But studies of the electronic structure of the chromium atom have determined that in fact it is 4s1 3d5. Similarly, for copper, we would expect to have an argon core 4s2 3d9. But similar to chromium, we actually have a configuration of argon 4s1 3d10. And the reason for this in depth goes beyond what we really need to know for Chem 110. But it's due to, in essence, the stability of partially filled subshells. And this is the level to which you need to know why there are exceptions. So when we look at the electron configuration, if we look at the orbital diagram, let's say for what we would expect to see for chromium, we would expect to see 4s2 3d4. Got one too many lines there. The reason why we get these half-filled subshells is because the electron-electron repulsion within the 4s subshell is greater than the energy required to promote the 4s electron to the 3d subshell. So in other words, this proposed electron configuration is greater in energy than this electron configuration. And that's again due to the stability of partially filled subshells. Fundamentally, it has to do with the symmetry that is obtained by partially filling the subshells rather than having a completely filled subshell and only an incompletely filled subshell. When it comes to the valence electrons of transition metals, iron has 8 valence electrons, the 4s2 and the 3d6. Normally, when we think about valence shell, these are the outer shell electrons that are valence shell. Because the d orbital is unfilled, those also contribute to the valence electrons. Now, in the case of zinc, the 3d orbital electrons are not valence because it's been filled. For the case of copper, the 3d valence electrons, or the 3d electrons are not valence because they've been filled. It's only when we have a partially filled subshell. In the case of scandium through nickel, their valence electrons include both the 4s and the 3d electrons. Let's take a look now at the periodic table. One way that we can organize the periodic table is based upon its energy. And so our energy is increasing as we go from left to right. And then the energy is also increasing as we go from top to bottom. So the orbital, the electrons that would be in the 7p orbitals are higher energy. These are our highest energy electrons, whereas those in the 1s are the lowest energy electrons. So we could, this is one way to organize the periodic table. However, this is not the commonly organized fashion. Much more common is to look at the periodic table and to have moved this set of elements beneath it. And in this case, we've put these elements, what we call the F block elements, beneath the periodic table. And now we can talk about the periodic table and its properties. So you need to be familiar with what we call the S block of the periodic table, the P block of the periodic table, the D block, and the F block. These are the same S, P, D, and F that we talk about when we talk about the magnetic, the L quantum number. So for a value of 0, 1, 2, and 3, we have S, P, D, and F. And hopefully you'll see that when we've looked at the S-type orbitals, that we can only have 2 electrons within them. There are 3 p orbitals, there are 5 d orbitals, and there are 7 f orbitals. When you take a look at the organization of the periodic table, keeping in mind that each orbital can house 2 electrons, look at the width of each block. The s block is 2 elements wide. And an s orbital can house 2 electrons. The p block is 6 elements wide. And with the 3 p orbitals, they can house 6 electrons. Similarly, the d block is 10 elements wide. How many electrons do you think could be housed in the d orbitals? 10 electrons. The f block is 14 elements wide. And there are 14 electrons that can be housed within an F subshell. So this is no coincidence. The orbitals, the quantum numbers themselves, dictate the structure of the periodic table. And from those quantum numbers, we can determine the electron configurations. Remember, when we look at the electron configuration of, let's say, the carbon atom, we've identified the N, the L value, and then we've identified the number of electrons. So these are all related to each other. The last thing that you need to be familiar with in terms of the periodic table and its organization is some naming that we have. On the left-hand side of the periodic table, we have metals. On the right-hand side of the periodic table, we have our nonmetals. And smashed in between those, we have the metalloids. And these behave similar to metals and also similar to nonmetals. They have intermediate characteristics. We have our transition metal region of the periodic table. That is our D block. You have halogens, which is the 7th main group. You have the noble gases, which is the 8th main group. The first main group we call the alkali metals. The second main group is the alkaline earth metals. And elements within a given group are going to behave similarly. So alkali metals behave similar to one another. Alkaline earth metals behave similarly to each other. The halogens behave similarly. The noble gases behave similarly. So you should be able to predict what elements would behave similarly to each other based upon the group or the family that they are in. So again, this would be a group or a family. And then this we would call a row or a period. That's it for this video in terms of the content. In the next video, I'm going to walk you through a couple sample problems. Thanks for watching.